Good afternoon and welcome to the College of Optical Sciences Colloquium series. We're very fortunate today to have Professor Axel Scherer here from Caltech, and we're actually very lucky. We had a little bit of a scheduling mix-up, and he actually flew out, got in a couple of hours ago, and is flying back. So we really appreciate him going through the effort to be here for this. And we told Professor Scherer that nobody would turn on the Caltech basketball game that starts at 4:45. So expect you all to hold to that. Professor Scherer is the Bernard A. Naches Professor of Electrical Engineering, Applied Physics, and Physics at Caltech. And he received his PhD in 1985 from New Mexico Tech, and I didn't know that, over in Socorro, working in the Microstructures Research Group at Belcor. After working at the Microstructures Research Group at Belcor, and he joined Electrical Engineering option at Caltech in 1993. His group is now working on micro and nanofabrication of optical, magnetic, and fluidic devices. He's co-authored over 300 publications and holds over 80 patents in the fields of optoelectronics, microfluidics, and new nanofabrication techniques. He's best known for some of his, or not best known, made his original large contribution in the area of VCSELs and other things associated with making small lasers, and now his group is largely focused on the integration of microfluidic chips with electronic, photonic, and magnetic sensors. And today he's going to be talking to us about nanofabricated silicon devices and nanosensors and nanospectroscopy.
Thank you. Thank you for the fantastic introduction. I'll hope to entertain you this afternoon by showing you some of the devices that we're working on at the moment in my group. And I'm going to focus in particular on devices made out of silicon, although we make devices out of many different materials. The people that actually do the work are shown here. These are my collaborators and graduate students. And basically, they will, they're focused on taking silicon and using it for nanosensors. We've been particularly interested in measuring metabolites in biomedical applications, and so we'll talk about that. The integration of electronics is, of course, something that happened over the last 50 years or so. We're seeing integration of fluidic systems, and we're seeing integration of optical systems that occur pretty much at the same time, and they're all fueled by lithographic construction of devices. What's interesting is if you take this approach of integrating electronics, fluidics, and optics, you can actually build systems where you can align these different functions on top of one another, which are multifunctional. And that's part of the reason why we're so excited and interested in lithographically producing devices. And everything I'll show you today are devices that are lithographically produced, with the exception of maybe some of the neural probes, which I'm still gluing together manually. Okay. So printing, or lithography, has a long history. It's made books cheaper, and it's made electronics cheaper, and we believe that it continues making things cheaper because you can get more functionality out of the same area. That's what drives Moore's law. And the idea is really that you can make devices smaller. So there is something called Bell's law, which I recently discovered, and that is a rule of thumb that basically says that every 10 years, a system, an electronic system, consumer electronic system like this one, every 10 years, you'll decrease its volume by a factor of 100. All right? And that comes right out of Moore's law. If you think about the device integration and miniaturization, this is the systems miniaturization. And what's happening nowadays is we have these relatively small systems that are very powerful, and Bell's law, I think, is going to level off, okay, for different reasons. Power supply, for example, communications or readout are going to ultimately limit the size of things, not the electronics. it's sort of instructive to see one of these systems. Here's a system that's made by University of Michigan. And the biggest part of the system is the battery. Okay, so the electronics is actually smaller than the battery. And what we're trying to do is make devices that are much smaller than this, that are microns in size rather than millimeters in size. And when we build these kinds of systems, we have to become more flexible in how we power them and so on. Let me also remind you of where we are in the electronics industry, the SIA roadmap. This is, I think, Intel's version of it. These are different processes that are coming online. 2013, we should now be somewhere between the 22 and the 14 nanometer process. It turns out you can buy devices that are on the order of 25 or 28 nanometers now in size. Probably can go down to 22. And the devices, are becoming progressively smaller. In 2015, we should make 10 nanometer devices commercially. In 2020, we'll be somewhere out here, maybe at 5 nanometer devices. One of the interesting things is that we've been sort of thinking in my group is, how do these devices that are 10 nanometers differ from devices that are 22 nanometers? And then how do the devices that we project will happen, how do they perform? And one very interesting thing that's happened already is we've gone from a two-dimensional world where a transistor consists of this flat piece of silicon with different dopants. We've gone into a three-dimensional world where we have fins sticking out and where we have fully depleted structures that we try to use where we inject electrons or holes electrostatically. So I'm going to talk about this today. So the first part of my talk will focus on this roadmap. Where is it going? Where have we come from? Where are we going? And what is silicon going to do once we make it with sizes down to about 3 nanometers? The second part of my talk, I'll talk about applications, and applications in the biomedical world. So when I came out of Belcore, we made these kinds of structures, the vertical cavity lasers. And then we decided to make two-dimensional devices like this one. This is a photonic crystal waveguide. And we thought originally that we would have to go to three-dimensional devices in order to confine light in an efficient way. And what was surprising to me was that we actually never had to go to the fully three-dimensional world. It turns out that by designing two-dimensional systems that have total internal reflection, that keep light within thin membranes, that we could do whatever we needed to do for many of the applications that we originally wanted to do. So we made these kinds of lasers. Here's a typical photonic crystal laser. Because it has a very low threshold, we can run it CW. We don't have to pulse it. And because it runs CW, it has a very narrow line width. So we can have line widths out of these lasers in the tens of picometer scales. And once you have this kind of very narrow line width, you can do spectroscopy. So the idea is, out of building devices that are efficient, you can start building systems that allow you to do certain things. So the first thing you can do is you can take one of these photonic crystal lasers and you can dip the laser into something. You have a lot of holes, so if you dip it into a solution, you should start seeing changes in the lasing wavelength, and in fact that's what we saw. So this is old data that we had. One of the interesting things was that we measured the mode volume of these lasers, and it typically is somewhere between 10 to the minus 18 or 10 to the minus 17 liters. So we can measure with this kind of a structure the refractive index of that kind of small volume. So it's already very enabling. One of the things that we've done over the last couple of years is we've gone away from this structure, and we started making structures like this one. We've gone into what people call the nanobeam photonic crystals. It turns out that nanobeams were developed by people. Actually, my former student, Oscar Painter, did a lot of work on them. And Marco Lonkar and people at Stanford. It seems like I'm competing with my former students a lot. But basically, there's a lot of, this is an interesting device in that it allows you to make a resonator without having a two-dimensional membrane. In this case, you simply have a one-dimensional wire. And in this case, you have a Bragg reflector that's built in by drilling holes through this one-dimensional silicon wire or gallium arsenide wire. So we like this kind of device because it allows us to make these kinds of very small, localized resonators with pretty high Qs. And it is a linear structure, so it actually allows us to take advantage of one of the properties of silicon, which is that it conducts. Silicon conducts as well as waveguides. Then we can heat up this device by simply putting current through it, resistively heating it. So you can make Qs of hundreds of thousands out of these kinds of structures. The light is localized in a very small volume. You can make lasers out of these. These are some of the smallest lasers we've made. They're made out of indium gallium arsenide phosphide. Here they are, suspended. And you see nice single wavelength emission, and they're nice lasers. What else can we do? Well, we can also build structures that are filters. So in this kind of device, we have a nanobeam resonator, and we have a heater on top of it. And this heater is actually on top of this nanobeam. It's separated from the nanobeam by a very thin silicon dioxide cladding region. The heater is made out of nichrome, so we put current through it, and when we heat up the nichrome, that also couples heat into the resonator, and it makes this resonator move. So it basically retunes the resonator as we heat up the device. Okay, so we can control the temperature by changing the heat, and that in turn changes the resonance frequency of our nanobeam resonator. We'll come back to this in a little bit. These kinds of devices can be used for many different applications. You can use them for tunable filters. You can also use them for sensors. And I'll talk about them as sensors in a little bit. Why are we trying to do this? Well, we're trying to add to what's already sort of a formidable set of technologies that people have developed for silicon photonics. You can basically make devices now that have up to 100 gigabit per second throughput with silicon photonics. One thing that's missing in silicon photonics, has traditionally been missing, is the light. We have very little. So far, we always have to couple in light from external lasers, or we have to wafer bond. We have to do things like that. So the commercial world has developed these kinds of chips. You can buy them from places like Luxtera. You can probably get them from IBM or many other places now. Pretty soon they will be commonplace. But what's missing is the light emission, and that's so far been the highest cost of the structure. It turns out when you talk to the people from Intel, they'll tell you 1/3 of the cost of the device is actually the light source. The other third is the packaging, and the third is all the electronics, with all the silicon electronics and photonics on top of it. So the question is, how can we get rid of this? How can we actually address and generate light on a silicon chip? And there are many different ways of doing that. You can have a wafer-bonded light source that's on top of silicon, and that can allow you to couple light into the silicon waveguide to light up the waveguide. You can make structures like this one. This is Connie Chang-Hausein's work, where she grows indium gallium arsenide phosphide structures on silicon, epitaxially. Or maybe you could change the way that silicon works, and that's what I'll talk about next. Maybe you can make silicon into a direct bandgap semiconductor. Well, it's been tried before, and lots of people have had this vision. Let me show you where we are at the moment with this idea. Well, we can make small structures in silicon. We can make small structures by etching and lithography. We can make structures down to, well, 22 nanometers. That's the roadmap. That's what we're supposed to be able to do right now. So once we have small structures like this, at these dimensions, silicon still behaves more or less like a bulk silicon material. You can make structures that are dense or less dense. They actually have some interesting mechanical properties. These are some of the silicon wires. We've made these little pillars, and we're probing them with this big, huge electrical probe. And you see that this wire is starting to bend as we measure the IV characteristics, and you see it starts moving around. And then when you lift up the probe, it snaps back to its original shape. Okay? So it's elastic. And here are some more extreme cases. The silicon, in this case, these are 40 nanometer wide pillars, and they're bent over. And this one over here, for example, bends almost perpendicular to its original orientation. Here you see the time lapse. You basically, if you look at the one that's over here, it's completely bent over, and then it becomes completely straight. You can get up to 25% elastic deformation out of silicon when you make it into this scale. Okay, in a typical bulk silicon crystal, you'd be hard pressed to get more than a couple of percent. So this is already interesting. Now, if you make structures down to 10 nanometers, you can see additional effects. You start seeing that the electrons are more collimated. But if you're not happy with 10 nanometers and want to make the silicon even smaller, then you have to play a trick. You can sort of, even to see these structures, you have to look at them in an electron microscope. This is a reflection microscopy image where we see the little whiskers sticking out. If you take silicon and you've made it to whatever size you normally can do lithographically, the good news is that you can oxidize it down to whatever size you would like to make, simply by putting it into a furnace and heating it up in an oxygen environment. Okay? So you can start with something that's 40 nanometers or so, and you can end up with something that is 3 nanometers, okay, where you have a thin whisker of silicon surrounded by oxide. What's even more remarkable is that this oxidation process actually self-terminates. It stops. So what happens is the silicon forms the oxide. The silicon dioxide is bigger than the silicon because it's got oxygen atoms in it. And so it forms this material with a very high compressive stress. Inside of the silicon, you have a very high tensile stress. And what happens is eventually the stress that is on the silicon dioxide pushes the oxide atoms so close together that you stop the diffusion process. And in fact, you see here these different curves. These are different sizes. This is work done by Fabian Pies's group in Stanford in 1993. They observed this. They saw that sort of terminated. We rediscovered it, and then we realized that they've already done it. But it's beautiful work that shows that this oxidation actually self-terminates, which means that you can build these kinds of small structures in a very predictive way. So we can make structures down to 3 nanometers by simply oxidizing pillars, and then we can measure them. So what we've done is we've built a bunch of different pillars. We've started with 35 nanometer or 50 nanometer lithographically produced pillars, and then we oxidize them down. And depending on the temperature that we choose, if we oxidize to completion, we get different dimensions of this little whisker. It turns out that it sort of stabilizes at about 2 nanometers. That's the smallest dimensions that we can make at the moment. Okay, so we have 2.89 nanometers here. the conducting structure, and it's surrounded by the oxide. What's interesting is this can be used directly in order to make a MOSFET. So you have a silicon whisker surrounded by oxide. All you need is a gate around it, and you have a transistor. All right. One thing that's interesting is you can see it light up. So you would not expect to get good luminescence out of silicon because it's an indirect bandgap semiconductor. But once you go below 8 nanometers, you start getting more and more intense light coming out of these very small structures. And that's because the electrons and holes are more collimated. They're now no longer randomly going in all directions. They're going down this wire in a very collimated way. And so basically you can increase the directness of your band structure. And in addition to that, these devices tend to have a very high tensile strain in the silicon. So if you do the calculation, it turns out that if you take a tight binding model calculation, the silicon band structure readjusts itself, and it gives you better light emission if you strain the silicon. So one of the good news is that we find electroluminescence. We have to create a p-n junction in order to make a LED, though. And the bad news is it's very difficult to make a p-n junction when your structure is only 3 nanometers wide. Okay, because this is a plot of the dopant concentration, the bulk dopant concentration that you would have to have versus the number of dopants that you would expect in the structure. Right? You rapidly realize that even if you heavily dope the material, you only have 3 or 4 dopants in the region, and that doesn't make for a good p-n junction. So what needs to happen in order to create these structures and make them electroluminescent is you have to have a series of gates. You have to attract electrons and holes by using electrostatics rather than by using chemistry. So it turns out that it's a more complicated device in order to make it with lots of opportunity of shorting out. That's why we only have a couple of data points that show real electroluminescence out of this. So you can make a structure like this. You can have some sort of a top contact and a bottom contact, and then you can make your P and your N parts of your device by having 2 separate gates. So we're getting to answer, I think, some of the questions of what's happening when we go down this roadmap, what's going to happen when we go below 10 nanometers in size. Silicon starts becoming mechanically different. Silicon starts emitting light, and it actually has a band gap that changes. So if I go back over here, notice that we look here at the photoluminescence spectrum. And as we change from 2.4 nanometers to 8 nanometers, we see this spectrum moving and tuning. That's because we're blue shifting the material as we shrink down the device structure. This is well understood. It's basically, this can all be modeled, and it's an easily understood process. One of the interesting observations is that we no longer have a band gap of 1.1 eV, but in this case we have a band gap of somewhere between 1.8 and 1.9 eV. Okay? So we can design silicon to have a different band gap. We can make the band structure different. And we can come up with maybe a device that would be fundamentally different from the traditional MOSFETs. Instead of having an in-plane device where carriers move underneath the surface of your silicon wafer, in this case you may have a vertical device where carriers move through this very little hole. And this is the way we make it. So we basically do all the metallization and then at the end put the contact on the top. This is what a transistor structure looks like in cross-section. We have several metal layers. These are the dark layers that they're then connected to different gates. This is what they look like. And we can get MOSFET characteristics and amplification and all of that. One of the interesting byproducts of making devices with a high band gap is that you can make them work at higher temperatures. So where silicon typically can't be used beyond a certain temperature, beyond about 200 degrees centigrade or so, we can now use this small structure and go to even higher temperatures. And in fact, you can go one step further and say, if I'm going to make a gate on top of my silicon device, I will have my little pillars sticking through a little membrane. That little membrane will be my gate metal. What I can do is I can design this gate metal in such a way that it also does something that is optically favorable. You can make this into a plasmonic material, where the gate can be used to sort of increase the field intensity of the light inside of the little holes. So all of these capabilities, you can imagine building a gate that doesn't serve only the function of creating or attracting carriers, but you could imagine having that gate also serve the function of concentrating light. It's like an optical antenna. This is one of the things we're working on. So we have made these structures with gold, and then we can look at what happens inside of this little silicon membrane. This is some preliminary results. So basically, all of this idea, taking silicon, reducing its size by oxidation, and then using metal to try to modulate the dopant or the carrier concentration, these all start looking more and more interesting. You can make ion detectors. These are ion sensors. By taking a very simple device, you have basically the silicon nanowire that is surrounded by the gate. And if you don't connect the gate, you just put it into a solution, then the gate will self-bias by having ions in the solution, changing the electrical potential of this structure. And you can then look at the IV characteristics of your source-drain conduction change. Okay, so in this case, the little transistors that are ion sensors are only 100 or 200 nanometers wide, and they can identify salinity in this case, potassium chloride concentration, or sodium chloride concentration. You can integrate those into microfluidics, so you can take a microfluidic chip, and then you have the silicon underneath it, and you can measure things. All right, let me talk about 3 dimensions. So far, we've talked about 2-dimensional patterning, pattern transfer, and we've shown that we can make structures where the silicon can be down to about 3 nanometers in size for the channel width of a transistor. What if we wanted to change that width? Not change it by lithography, but change it during the processing. What I'm talking about is you can take a silicon, etch, and you can etch the silicon different ways. You can make silicon, you put it in an etching machine, you have basically a mask that's given, and you can undercut this silicon. Okay? If my student gave me something like this, let me shut this off. Oh, here it is. Okay. If my student made a device like this, I would probably not be very happy because obviously the etch gas is a little bit too high. It's more reactive than it's supposed to be. And so you wouldn't really want this. However, if you change the etching condition, you can actually recover during the etch the original shape and structure of the silicon. So you basically can make a little divot into the silicon during the etching process. You can undulate the silicon. You can etch in and out and in and out and in and out by doing a series of changes in the ion etching chemistry and the voltage that you apply to your bias voltage of your silicon etching machine. You can make structures like this. You can make a structure that looks like this. You can have it go in, and then out, and then in, and then out. What's interesting about this structure is that silicon is about 10 nanometers up here, maybe on that scale after I oxidize it. It's only about 2 nanometers over here. And then it goes back up to maybe 5 or 6 nanometers. Then it goes to 2 nanometers. Now remember, when we think about the band structure, the silicon in the band structure here will have a higher band gap than it does up here or down here. And so that means you can make a device where you can change the band gap of the silicon in the vertical direction. All right? And this kind of structure, if you now put a current through it, should be a resonant tunneling device. Okay? You can make this complicated devices. We can make several changes and so on. So this is, you can oxidize it. You can take the photoluminescence spectrum, and you can see that if you use the smallest structure, you end up getting a shorter wavelength emission, as you would expect from the blue shift, at around 600 nanometers. The bigger devices would be 800 nanometers. What's interesting here is you can tell the difference between 2 nanometers and 2.4 nanometers for the quantum dot size that you've created. This is what the structure sort of looks like when you look at it in the TEM. So making these kinds of structures may give us an opportunity to build new types of electronic devices out of silicon, okay, where we, instead of changing the chemistry, we change the geometry. So we can take a device like a resonant tunneling device. You can simply make it out of silicon. And in fact, when we do that, we end up getting these resonances. This is just a 2-terminal device where we simply take this structure and we put a current through it, or put a voltage through it. And as we change the voltage, the current goes through these undulations. Okay, so you get a negative differential resistance and all of that you would expect. Sort of a very interesting device. You can build structures out of silicon without changing to gallium arsenide or any other material. And you can use, I think this is the first time that you can show that you can use the geometry alone in order to control the behavior of the device. So, silicon changes profoundly as we make the devices smaller. We see more luminescence efficiency. We see mechanical, elastic deformation that is very large. We can build structures that function because of their high surface-to-volume ratio. And we can even do what we call geometric bandgap engineering. So now, I have gone through half of my talk. Now I'm going to talk about applications of this. All right. So we talked about the scale of things. So if we go from tennis ball size to atom size, we go through the spectrum. And I mentioned that we can make transistors with channel widths of somewhere on the order of 3 nanometers. We can make little holes that are about 2 nanometers lithographically. Okay, and IBM could show the xenon atoms, placing them in accurate positions, and that's on the order of 1 nanometer or so. Okay, so it's interesting. This plenty of room on the bottom is slowly getting populated. So what does that really mean in terms of applications? Well, I'm going to talk about a particular application that I'm interested in, and that is the medical application. I'm thinking about trying to build systems, like many of you are, in which we can use optics or miniaturized devices to understand what's happening inside of the body. Okay? And you can do this either remotely, or you can do it by putting something into the body and that then relays out what it's measuring. You can do this by putting something at the end of a needle and sticking it in, or you can have a wireless device that's implanted. And we'll talk about all of these. So there are 3 different ways to measure what's inside of your body that I know of. I mean, there are many others, I'm sure, but let me give you my 3 different ways that I can imagine. One is you punch something into the body, and like a needle, and you extract blood or something, whatever material. You biopsy, whatever you decide to do. Let's say it's a blood drop. You get the blood drop out, and then you analyze it in a big system like this. This is one way to measure what's in the body. And that's typically what we do. When I get my physical in the doctor's office, they take a bunch of blood, 5 milliliters or whatever it is, and they'll do this kind of measurement. Okay. Now, I can address the fact that this costs $1 million or whatever by making it smaller, but it's basically this system will always have to extract some material. Okay? It's particularly good for disease diagnostics and genetic testing when you don't want to have a continuous data flow of what's happening in your body. Okay? So we would ideally have a device like this, a handheld operated, battery operated device that can measure your health status. Okay? You go in there and it makes some strange noise, and it would measure whether you're ready, to go to the emergency room or not. Okay. So this is one modality, and we've actually built devices like this. So let me share with you what these devices look like. These are big devices. We've actually done this with the help of the Bill and Melinda Gates Foundation. We built these kinds of boxes. Basically, we do it in a collaboration. Everything I do is in a collaboration. In this case, I collaborate with David Baltimore, who is a Nobel laureate, so it's good to hang out with him. And Greg Tsongalis, who is a clinician. He's a real pathologist who runs a pathology lab. So he tells me what really needs to be done. And that's me. So basically, we have developed an instrument which is called a PCR instrument. It's a polymerase chain reactor. It heats and cools samples very quickly, and it measures for DNA. So you look for a match in the DNA. And the idea is to build something that is really inexpensive, because the Bill and Melinda Gates Foundation wants to use this instrument to measure things in the developing world. They want to measure pathogens, malaria, HIV, TB, things like that. So this has to be really inexpensive. It has to actually, what's interesting for us is it has a particular part which measures fluorescence, and that's the optical part. That's, of course, what makes me happy. I like the optics part. Fluorescence detection, usually, you use a laser or an LED or something like that, and you generate light fluorescence. And the interesting thing is the fluorescence occurs more efficiently in most of these fluorophores when they're inside of the DNA double helix. And so you can determine whether you've amplified DNA or not by simply looking at fluorescence intensity. So one of the things that's interesting is this kind of instrument costs us about $500 to build. If you bought a PCR machine, it would cost about $10,000, probably more than that. And it would take about 90 minutes to do an amplification. And it turns out, if we build our own, we can do an amplification 30 times heating and cooling in about 35 seconds. So it's actually a lot faster. This is the optics, light pipe coming in. Everything's sort of a waveguide optics system. It allows us to not have the alignment problems that we normally have to struggle with lens systems. And we can start measuring pathogens. So we're measuring different pathogens, and we can identify diseases. Hopefully, this will lead us at the end of next year to a device that actually can be produced for a couple of $100s to meet the needs of the developing world. Okay. Now, there's another way of measuring something inside of the body, and that is if I stick a needle into the body. I have my electronics outside, whatever measurement system outside, and I have the needle with a sensor inside, and I simply stick the needle in. This is what you would do in this case. Well, One thing you can do if you had a needle in the body is you can build on that needle some resonators. And you can measure spectroscopically what's happening to the surface of those resonators with time. So you can measure binding chemistries. And so silicon photonics, about 10 years ago, or a little more than 10 years now, gave us the opportunity of building silicon resonators with pretty good accuracy with high Qs. All right? So we can take a silicon resonator like this, we can cover it, coat it with some antibodies that allow us to selectively bind certain proteins, and we can do a label-free test that way. And this is, people do this. Actually, there's Genolite is a company that's making these kinds of devices, and they'll sell them to you. Now, we actually like this resonator better because we can heat it, and this is what it looks like in terms of this is the optical mode intensity. And we can make a resonator like this that's next to our feed waveguide that basically can tell us what the refractive index is of the material that's surrounding this resonator. So we basically can look at this structure, and at the same time we can heat the device up. So why do we want to heat it? Well, if we bind something, then we also want to know at what temperature it desorbs. We want to actually have a calorimetric measurement that verifies that we're binding the right stuff. So if we can measure the temperature at which the thing that we bind goes away, we can verify whether it was what we were thinking it was or not. Okay. So we're building these kinds of structures. The idea is, of course, to make the smallest possible device with the sharpest possible peak. And we typically struggle to try to get Qs on the order of 100,000. We can actually make sensors out of this, gas sensors, which can measure gas concentrations down to about 8 parts per billion or so. And these devices can work very quickly because they're very small. So you can heat and cool them. 30 nanometers shift corresponds to about 430 Kelvin in temperature change. We can heat and cool them with that temperature change within microseconds. So we can actually do very fast response. We can make many of these resonators, and we can build a system that now can look for different types of proteins or RNA fragments that are in the bloodstream that allow us then to identify what's happening inside of the body. Now, in this kind of a system, you would still have a laser. That would be outside. You would have some needle that would allow you to couple that light in. And then you would have the silicon chip that has all of these sensors on it. And the idea is that all of these sensors have to be small enough that they can fit into the vein of a human. So they have to be on the order of, not more than 100 microns for the whole system. So if you make IV measurements, this is intravenous measurements, not current voltage measurements. The big advantage of making these kinds of measurements in the intravenous approach is that you probably have a bunch of needles sticking in you if you're in the intensive care unit anyway. And so an extra needle may not matter too much. If you wanted to have this system continuously monitoring you, it would be a big inconvenience. But for a particular case of having something in an intensive care situation, this actually works pretty well. You could have feedback if you give somebody chemotherapy or platelet therapy. You could have feedback of the different proteins. No wireless system is really needed for this kind of application. And so most of the bulky optics can be outside. Okay, so this is the low-hanging fruit, if you will. What we, at the end of the day, really want to do is we want to deal with the medical care at the point of care. All right? So the point of care, at the moment, is usually not even at the doctor's office. It's at the hospital or at the blood lab. Okay? Somebody's measuring something there that's actionable. We want to move that first towards the doctor's office, which means that we need to make these little boxes that I talked about earlier. But then eventually we want to make that point of care be in our body. We want to measure something right where we are, because we are, after all, the point where the care should be coming. And so one of the things that is very compelling, especially for chronic diseases, is to have a sensor system inside of the body talking to some sort of a reader that's outside of the body that can then be monitoring our health status continuously. We want to measure continuously what's going on. Okay, that would allow us then also to figure out what the baseline is. And so we can do that. So it turns out most modern implants are typically millimeters in size. So this is just an example of a oncology implant. We would like to make these devices microns in size, or hundreds of microns initially. Okay? What we need to do is we need to somehow power these devices. We need to somehow read out what they're telling us. And then we need to figure out how to do the actual sensing. Okay? All of these things should be done. They should be self-contained. And so in our first generation of devices, we assume that you have some sort of an optical solution. Now, as you probably gathered, I like optical solutions. So there may be a wireless solution that is different, that is better. I really don't know. Maybe RF powering is better. Maybe inductive powering is better. But I don't know how to do those things. So I like to build something with an optical solution. So the best optical solution I could come up with is a photovoltaic cell that allows me to power the device. Photons come in. I know exactly what wavelength they're at because I'm going to have my laser pointer that I know what it is, exactly the right wavelength. And I can get a pretty good solar collector that then can convert this into current and voltage on the chip. And then I'll have some sensor. That sensor could be electrochemical, it could be optical, it could be many different things. And then I have a data communication system. Maybe I have a VCSEL, a vertical cavity laser. Since I like vertical cavity lasers, maybe we should use that. And this is the system. It's basically, you have a vertical cavity laser, you have the power supply, the photovoltaic, and then you have the electronics on the other side. You all glued together. Okay? And all you need to do is wire it up. That's, not trivial, but it's possible. We actually use a focused ion beam system to do that. Now, first of all, you want to figure out what wavelength you want to operate at. So the most favorable wavelength in terms of low absorption would be right around the 1 micron region, somewhere in the near infrared. Okay, because at the longer wavelengths, you start getting water absorption. Shorter wavelengths, you get absorption in the hemoglobin. And so basically, this wavelength seems to work well. And it also turns out that you have good vertical cavity lasers available in this wavelength range, and so on and so forth. Why do we want to avoid absorption? Well, it's not because we can't build a big enough laser to put in the power. It's because we don't want to heat the tissue while we're doing the measurement. Okay? So we want to minimize absorption losses. I don't care about scattering losses. Scattering is fine. But absorption is something that will heat up my cells, and I'll start boiling them. So I don't want that. Okay, so how can I generate power? Well, it turns out if I make a photovoltaic cell, and this is now 35 microns by 25 microns in size, I can get a considerable amount of power out of it. I can get 250 microamps out of this by shining a laser on it. Okay, it's actually surprised me. I didn't think I'd get that much power. But anyway, it turns out that if you boost the voltage, then you take a huge hit in the current. So if you have to go to 1.5 volts, then you're obviously much lower current. But you can build something out of this 35 by 25 micron photovoltaics that basically allow you now to build like a series of these photovoltaic cells that allow you to generate now power on the chip. Then you want to take that power, you want to run an electronic circuit, and then you want to transmit the information back out. And that's where we get into the chicken experiment. So I have pieces of chicken fillets on my laser tables. My students, my postdocs, put them there. And first I was sort of I thought it was unusual. But anyway, so there's the chicken fillet, and the laser is the chip with the laser in it is underneath it, and we're measuring what comes out. Okay, and we identified that we can transmit through 5 millimeters of chicken fillet. Okay, now what that translates into in the human body is still left to be found out. But in any case, the good news is we can transmit through chicken. So the next step is to then encode what we need to transmit. Well, we don't want to just have intensity as the transmission medium. We want to use frequency, so we need to have a voltage to frequency converter, right? So that's pretty straightforward to build. Very easy electronic system. Very compact. Everything can be compact. Now remember, in this kind of system, there is no battery. We actually do not have a battery on board. We actually power the device, and the moment it gets power, it turns itself on, and it then gives us this bit stream, okay, of information. And then we can get, for example, in this case, an EKG signal from a rat. It goes into a digitized format, and then it comes back out. We can actually see very good fidelity of getting back the information that we started with. So what are we going to do with this? The first application that I think 10% of the population can relate to pretty soon is a glucometer. It turns out we all have lifestyle issues that cause us to become more predisposed to diabetes. And so glucose measurements are becoming a serious problem. So if you look at basically out of the U.S. population that's old, 65 years or older, I'm getting there slowly, 26% had diabetes. Okay, and it turns out it's a very sad story. We actually have a lot of people that are pre-diabetic. And so these people should be testing themselves to minimize the damage that gets done during due to the glucose. And it turns out that the way we do it now is we take finger prick samples. So diabetics have to prick themselves when they're before the meal or after the meal. And basically you end up having a lot of pain associated with that, as well as sporadic measurements. So the excursion coming from the donut that I just ate may be at a different time than when I'm testing myself, right? So it naturally is helpful if you could have a continuous monitor. In this case, you would simply have some glucose measurement. So the first glucometer that we built looks like this. So this is actually a big thing. This is a USB connection that we made on top of a silicon structure. This is the glucometer, and it's relatively large. It's about a centimeter by a centimeter. It has about 100 different potentiostat circuits, so we ended up identifying the best one from this. We built current-based potentiostats, and then made our second device, which was this one. So this is now 2 millimeters wide and about 5 millimeters long. And it has a glucometer, a data communication laser, and a power supply all integrated with it. And the actual potentiostat circuits are very small. They're within 100 microns or so in size. We can get very good results out of these devices by using surface to volume ratio approaches that we talked about earlier. And we can measure glucose. So in this case, you can see the different concentrations of glucose. You can see different curves that come out of this potentiostatic measurement. Okay. The good news is that once we build this potentiostat and we start measuring glucose, we can do that in a relatively small format. And we believe that we can shrink the devices that are now 2 millimeters wide even further. Okay. This is what the device does over a long period of time. You can measure it up to 6 weeks now. And anyway, this is the next generation device. This is essentially a couple of 100 microns in size. Okay. And the idea is here that we can shrink all the components and start building systems that are really all integrated systems. We started putting them into rats. Here's a poor Wistar rat that has these devices in its muscle tissue. Here's a typical device. And we see actually that there's surprisingly little scar tissue formation. So, small is beautiful, in my opinion. Small is beautiful because, first of all, we can limit the electromagnetic interference. We're all worried about electromagnetic interference. Now, you probably aren't, but anyway. It allows us to isolate the system. So we don't have a good antenna because it's too small. Okay. The neat thing about making the devices small, especially if they're implanted devices, is they move with the tissue rather than with respect to the tissue. So if you have a large device, it has its own inertia. It will move in one direction, and then the tissue rubs against it, and it gets irritated. We can put these devices into more precise locations simply by injecting them. We can avoid having to do surgery. We just have an injection system that allows us to put these things in. They can be less expensive because, after all, if we make millions of them out of the same wafer, then we can make them for cheaper. And if we measure something very locally, maybe it'll give us more interesting results. And there's another sort of a final interesting byproduct. By making something smaller, you decrease the potential toxicity. Okay. So all of these ideas point us towards making smaller and smaller devices. Okay. One of the particular applications of these small devices, in my opinion, is going to be understanding the brain. The last, I guess, unexplored space that we have no idea of how it works. I mean, some people have an idea, but I don't. Okay. How do we think? Why do we think? What is consciousness? Those kinds of questions. Ultimately, we have to build a tool set that allows us to explore those questions. And this may be one of the parts that may be able to be used. Now, why would we want to have data communications that's optical? Well, it turns out that if you think about it, the bandwidth that people really need in order to study something as complicated as the brain has to be ultimately in this range of gigabits per second. Okay. It turns out, I think, naturally, 5 years from now, people will be going away from the electronics simply because they're too bulky and because they have too much crosstalk and because they can't give us the information, data, the bandwidth that we ultimately need. Okay? So what we have now are these structures that sort of look like pitchforks. They have these little needles that are then connected to a bundle of wires that are coming out. And this cannot be used for gigabit per second data communications. All right? So it turns out that I think we will be ending up using optical communications regardless of whether we want to or not. Okay? So why not start there? Say, let's build something that's an optical data link right off the bat. Okay? And that's what we've started to do. So the hope is that we have fiber communications not to the home, not to the chip, but to the brain. All right? I don't know what that really means ethically, so let me not go there. But in any case, this may well be the way that we must go if we were to understand the brain. Okay. And this may be some of the solutions. This would be, for example, a little neural chip that in this case has 4 channels that work at 50 kilohertz, and they basically connect it with a vertical cavity laser. So there's a lot of opportunity there, I believe, of miniaturizing, shrinking, and taking advantage of all the things that we've learned over the years from data communications and telecommunications to start using them in these very small devices that are now free space communicating through the tissue. All right. We can go one step further. We can build little devices that can release drugs. Maybe if you have a brain tumor, you have the patient undergo surgery. At that point, after the surgery is done, maybe you want to put something in there that allows you to release drugs so that you don't have to have another surgery when you have a malignant tumor again. So this would require you to have very small, very local delivery systems. So I hope I've shared with you a glimpse of what I think we may do in the future. These are some of the smallest structures that we've made, 2-nanometer structures. And I'd like to thank you for your patience. I'm sorry that I went over.